this quantum annealing and this D-Waves machine is built just to solve this combinatorial optimization problem. So, this quantum annealing machine from D-Wave is optimized to solve exactly that kind of problems, like traveling salesman problem, vehicle routing problem. So it's already quite optimized, I would say. And also we have a larger number of qubits. In the case of IBM's machine or Google's machine, we have a bit different paradigm. So it's not quantum annealing. So there are these circuit-based models in which we just build a circuit with using quantum gates like Hadamard's gate or some rotation gates, for example. And there are also some quantum algorithms that can solve this kind of problems, these optimization problems, like QAOA, for example, or VQE. So in general, variational quantum eigensolvers, variational quantum algorithms. We've run experiments with these algorithms, but it turned out that we are only able to achieve some results for up to, let's say, 5 nodes. 5 nodes and maybe 1 or 2 vehicles. So very, very small instances. The reason is that we have very small number of qubits. And as you can see, we have these binary variables in which we have several indices. So, so basically, each of these binary variables corresponds to or should correspond to a logical qubit. So currently these quantum computers from IBM and Google are still not large enough in order to just give meaningful results for this quantum algorithm that we developed. It's an interesting thing that, and it's good to know that there are also some other, let's say, QUBO formulations for vehicle routing problems. So this is not the only one. So I'm not sure, Kevin, if I'm allowed to share my slides one more time. I can just for a minute, I will present a table that I haven't presented yet because it was included in the extra slides that I had later. So these are just examples of these different QUBO formulations, right? And in some cases, we might have smaller number of qubits. There's also a comparison of the approximation ratio for various solvers, but this is also an interesting table. So here we have the solution partitioning solver and the full QUBO solver that I've introduced today. And we also compared the required number of qubits that we need. So as you can see, in case of the solution partitioning solver or full QUBO solver, we need more or less n square number of qubits, or this is the order of magnitude of qubits that we need. So if you know, in case of IBM's or Google's machine, we have only just so I think that the largest IBM's machine have now 127 qubits. So it means that we might need to just solve, let's say, up to maybe 10 instances with, let's say, maybe up to 10 nodes, 10 customers. So that's the upper bound. But I'm not sure if this largest machine from IBM is available. So that's why currently this quantum annealing machine from D-Wave seems to be better at the current stage, but it may change in the future.
Awesome. So any other questions right now?
I was just curious, what was the size in qubits of the largest experiment that you ran on actual hardware?
On yes, on quantum machine. Let me go back. I'm not sure if we have it on our slides. Yeah, so there was QUBO solver. I cannot say. So for sure it was for, let's say, so here we have the results. It was only for, let's say, 2 vehicles, but I'm not sure. I don't remember. I can check it later. I don't remember what was the number of customers. But yeah, we had only we had only 2 vehicles here, right? So it was really small instance as well. But maybe there were, let's say, maybe up to about 10 customers, 10 nodes, and with 2 vehicles. But you can see that so based on the definition of these binary variables,